Friends, let us continue with the lecture 12. Where we are going to talk about the failure domains in system reliability. This is lecture in module 2 on system reliability or reliability theory on the online course Risk and Reliability of Offshore Structures. We already said for a series system and a parallel system, one can easily estimate the failure domains. So, let us revise for a parallel system which consists of n components. N components, the system fails if all its components fail. Therefore, the failure domain is given by, as we saw in the last lecture, for a parallel system, it is actually intersection of the component failure domains. I equals 1 to n, n is the number of components, Gix less than or equal to 0. That is the equation. Now, let us try to understand the failure domains of series systems and parallel system graphically. So, we know that series system failure function we know the failure domain of the parallel system. Let us try to understand this graphically. One is of course the intersection of the failure domains of different subcomponents, other is the union, okay? Because the failure condition for a series system is if any one fails, the system fails, whereas for the parallel system is if all of them fail, the system fails. Therefore, accordingly we have formulated the failure domain, we have given the governing equation for Gfx as we saw in this lecture and as we understood in the last lecture. Now, let us try to understand how the limit state function looks like for a failure domain of series system and that of a parallel system consisting of, let us say, 3 components. Okay. Let us say n, the number of components is 3. Okay. So, in the figure the hatching along the limit surface will be done, so that it indicates the region in which the corresponding limit state function is lesser than 0. So, kindly pay attention to the figure shown in the screen now. The figure shows the failure domains for a series system consisting of 3 components. One can see here G1 of x is equal to 0, which indicated by this line, the failure domain is this. So, this is the area which is the failure domain. Similarly, G3 of x is this line, the failure domain is indicated here, and G2 of x is this red line, the failure domain is indicated here. We know for a series system consisting of 3 components, it is a union of all of them. So, the hatched portion actually shows the failure domain of a series system with 3 components x1, x2 and x3, or G1 of x, G2 of x and G3 of x being the limit state functions of 3 independent components. Okay. Similarly, pay attention to the figure shown on the screen now. This figure shows the failure domains for parallel system consisting of 3 components. You can see here G1 of x is the limit state function for the first component, G2 of x is the limit state function for the second component, the hatched portion shows the failure domain. G3 of x is the failure domain for the third component, the hatched portion shows the failure domain. And just now, as we saw from equation 1 in the blackboard here, the failure domain is an intersection of these failure components. So, the hatched portion becomes the intersection of this failure domain, this failure domain and this failure domain. Okay. So, this becomes an intersection of all the 3. Therefore, for a general system, failure domain can be given by cut set formulation. Let us say failure domain can be written in two ways, Let us use the cut set formation. For the cut set formation, the failure domain is given by U of m intersection of I element of Cm and the failure function which is Gi of x less than or equal to 0, where Cm is the mth cut set. Now, the safe domain for the general system with cut set representation is defined by the path set formulation. Okay. So, that is going to be the safe domain, which is going to be over I intersection of I element of Pi with G of x greater than 0, because I am talking about the safe domain. Equation number 3, where Pi is the ith path set. Now, let us try to understand this dialog or argument with minimum cut sets. So, for a general system, failure domain is given by the union of minimum cut sets. Is it not? What are the cut sets in this case for our example? One is C4, which is 2, 3, 4. Other is C5, which is 1 and 4. These are the minimum cut sets we have. The failure domain was shaded in the figure as you saw in the screen for some assumed component limit set surfaces. Therefore, the problem of system reliability now can be stated. Probability of failure can be given by G f of x ds, which I call as equation number 4. One can always say alternatively probability of failure can also be given as, or 1 minus probability of failure can be given as integration of bar of G f of x. So, pay attention to the figure shown in the screen now. We are now marking the failure domain for the general system, which includes the minimum cut sets C4 and C5. So, one can see here the shaded region which includes C4, the failure domains, and G1 of x, G2 of x, or G3 of x and G4 of x and G2 of x, or the limit state functions assumed for events 1, 2, 3 and 4. Okay. So, the shaded region shows the failure domain. You can see here G1 of x has got failure domain this surface, G2 of x has got a failure domain this way, G3 of x has got a failure domain this way, and G4 of x has a failure domain this way. So, the intersection, the union of this is going to give me the failure domain of the general system. Okay. Having said this, let us extend our discussion for first order estimates of this failure. Now, in order to compute the system reliability, one must be able to compute the probability of the union of events, be it system series systems or subsystems. So, if you really want to find the probability of failure or to compute the system reliability, one need to estimate the probability of union of series systems or subsystems or probability of intersection of parallel systems or subsystems. Okay. Now, for a series system, probability of failure is given by probability of union I equals 1 to n G I of x less than or equal to 0. Call equation number 6. After applying to the approximate transformation u to u of x, after applying the approximate, let us say appropriate, okay. After applying the appropriate transformation, u as u of x to the standard normal space, one can find the probability of failure approximately as probability of union of I equals n G of I of u less than or equal to 0. When there is an approximation due to mapping of non-normal variable occurs, when there is an approximation of mapping of non-normal variables to the standard normal variable space occurs, then one has to linearize G of u equals 0. at the design point for the ith limit state function. Now, this can be done using Taylor series expansion, so in that case G I of u will be approximately equal to G transpose u I star u I u minus u I star, which is further equal to G I of u I star minus alpha I transpose u I or u minus u I star, which can be further written as G I u I star beta I minus alpha I transpose u, let us say set of equations as 8, where u I and beta I are the design points and reliability index of the ith component. Obtained from first order reliability methods applying to the component. The corresponding unit normal vector to the limit surface the surface is actually G I of u set to 0 at u I So, now in that case the probability of failure will be approximately equal to probability of intersection union I equals 1 to n beta I or beta I minus alpha transpose u, which is less than or equal to 0, equation number 9. Now, dividing both sides of the inequality by the positive scalar, let us say by dividing with positive scalar, which is G I u I star one can define as Zi minus alpha transpose, which is approximately n of 0, which is a standard normal variable. With 0 mean process. In that case, probability of failure is given by probability of u I equals 1 to n Z I less than or equal to beta I. Okay. So, with the help of rotational symmetry, of the standard normal space, which is actually used when you are transforming the non-normal variable to the normal variable, one can use the De Morgan's law. So, in that case, okay, to get probability of failure, in that case probability of failure is given by probability of Z I less than beta I, which is equal to 1 minus p of section of I equals 1 to n Z I greater than minus beta I, okay, which is further equal to 1 minus p of intersection of I equals 1 to n Z I less than or equal to minus beta, which I call as equation number 12. This can now result to easily, because I have a very interesting argument on the normal variable here, which can be simply 1 minus beta and R Z, where phi n of beta R Z is actually the joint normal cumulative distribution function, joint normal cumulative density function CDF with the correlation matrix R Z, which is evaluated at beta, which is given by different indices beta 1, beta 2, beta n transpose. In the present case, the correlation matrix is identical to a covariance matrix because of the normal variables. In the present case, the correlation matrix is identical to the covariance matrix. Because the variables are standard normal. Therefore, the correlation matrix is given by RZZ is nothing but which is A UU A transpose, nothing but A transpose. Equation 13. The off diagonal terms in this case, the ith row of A is actually alpha I transpose and will be actually unity. This is due to the definition of the variables. Okay. The off diagonal terms of RZZ are given by Zi Zj is alpha I transpose alpha j. Equation number 14, which quantifies the correlation between the failure modes I and j. So, equation 14 quantifies the correlation between the failure modes I and j. Okay. Now, also friends, please understand, the unlike the reliability analysis component level. So, in component level reliability analysis, the unit normal vector is of secondary importance. Due to the rotational symmetry of the normal space. In system analysis, you will see that the relative directions of the unit normal plays a significant role. Which are given by alpha I and alpha j play a significant role. Okay. That is the difference actually between the component level and reliability level in analysis. So, for a parallel system, the probability of failure is given by probability of section of I equals 1 to n g I x less than equal to 0, equation number 15. Now, this can be approximated as follows. So, I say probability of failure is probability of intersection of I equals 1 to n, which is g I of x less than or equal to 0, which is approximately equal to probability of intersection of I equals 1 to n of another set of variable which is u less than 0, which then can be approximated as probability of intersection of I equals 1 to n, which tells me the reliability index beta I minus alpha I t into u variable less than or equal to 0, which can then approximated as probability of intersection of I equals 1 to n, which is z I less than or equal to minus beta I, because I am transforming this into an equivalent normal variable space, equation number 16, which will amount to phi of n of minus beta r z. So, you already defined beta and r z z in the previous explanation. Okay. I already said beta and r z is a correlation matrix. So, the same definition applies here. So, since we have transformed the variables from x to a normal space u, I can apply this algorithm and get my probability of failure is nothing but the phi function of the two variables beta and r z z. Therefore, friends, from these two lectures one can easily understand behavior of a general system can be modeled either as a parallel system composed of path sets, with each path set acting like a subsystem of components in series, or vice versa. First order approximation for general systems reliability is based on the cut set formulation, which is now discussed. A similar approach can also be developed using a path set formulation, which I leave it to you for the self study. In order to estimate the probability of failure of a system using the cut set formulation, one need to evaluate the probability of failure of each system. So, let us talk about that. So, we are trying to estimate the probability of failure of a general system using cut set formulation. So, one need to know the probability of failure of the system, which is given by probability of u m section I element of C m of g I x less than 0, equation 17. Now, let the event be E m, which is intersection of I element of C m, which is then extended on the failure domain g of x less than 0. Now, E m is actually the event that the parallel subsystem which is represented by the cut set when C m fails. Okay. Therefore, probability of failure can be now rewritten as probability of UM EM. Okay. Equation number 80. So, as per the inclusion exclusion of set theory, one can derive the following statements. So, further probability of failure can be then written as probability of UM E1, which can be further read as probability of E1 union E2 union, keep on going as NE, which then can be written as I equals 1 to NE of probability of EI minus summation of J equals 1 to NE summation of I equals 1 to J minus 1 of probability of EI EJ. So, in this argument NC stands for the minimum cut sets. Identified from the general system. Now, the above equation can be solved by summing the probabilities of failure of each cut set. Let us say summation of I equals 1 to NE probability of EI along with the probability of failure of every possible intersection of cut sets. Okay. So, the above equation is now solved by summing the probabilities of failure of each subset, each cut set given by this expression along with the probabilities of failure of every possible along with the probability of failure of every possible intersection of the cut sets identified, of course using appropriate sign. Okay, that is very important. It is an algebraic summation. For the example we are discussing, two cut sets were identified. What are they? They are C4, which is 2, 3 and 4, and C5, which is 1 and 4. Therefore, let E4 and E5 represent the events associated with the parallel subsystem where the cut sets C4, C5 fail. Okay? I should say respectively, because E4 is associated with C4 and E5 with C5 respectively. Then one can say E4 is nothing but, that is nothing but related to C4, therefore 2, 3, 4 are there. Therefore, I can say G2 of x less than equal to 0 intersection G3 of x less than equal to 0 intersecting G4 of x less than equal to 0, that is going to be E4, and E5 obviously in the similar pattern is E5 compress of C5, so 1 and 4, so one can say G1 less than 0 intersecting G4 less than 0. Okay. Call this as equation number 19. Therefore, probability of failure is given by probability of failure is P of E4 plus P of E5, because these are the two events from the cut sets, minus P of E4 E5, which is essentially derived based on the rules of probability what we studied in the first module. Call equation number 20. So, for explanation, PE4 is nothing but phi of 3 which has arguments of reliability index B4 and R4. P of E5 is approximately phi of 2 of minus beta phi R5, and E4 E5 is probability of phi 4 minus beta 4 phi beta 4 phi. Okay. Equation number 20, where beta 4 is beta 2, beta 3, beta 4, R4 is the correlationship matrix which is going to be 1, alpha 3, alpha 2, alpha 4, alpha 1, alpha 2, alpha 3, 1, alpha 4, alpha 3, alpha 2, alpha 4, alpha 3, alpha 4 and 1. Beta phi, beta 1 and beta 4, and R phi 1, 1, alpha 4, alpha 1, and alpha 1, alpha 4. Beta 4 phi, beta 1, 2, 3, 4, and R 4 phi. One, alpha 2 1, alpha 3 1, and alpha 4 1, alpha 1 2, alpha 1 3, and alpha 1 4. Again 1, alpha 3 2, alpha 4 2, and in this case alpha 2 3 and alpha 2 4. Again 1, alpha 4 3 and 1, alpha 3 4. That is going to be my R 4 5. So, friends, in this lecture we are able to estimate the probability of failure, for example, from a minimum cut system taken from the general system, applied the mathematical simplification of converting the non-normal variables to a normal variate space, and we are able to estimate the probability of failure using the rules of probability theory what we studied in the first module. We will extend this discussion further and try to understand how this can be further in detail be done. Then we will take up this application later with a numerical example. Thank you very much.